in Scotty's. Oh, now we are on live on YouTube, I guess. Yeah.
Not quite. There's a bit of a delay. Okay. Yeah, we're good on YouTube now. All right. All right,
yeah,
you
we
can get started now.
I'm sorry, Professor. Can you please start?
Can you hear us?
Can you hear us first?
Yes.
Oh, you can start.
Maybe. Share the screen.
Oh, yeah.
Scotty, can you please give us access to sharing the screen?
All right, you can do it now.
Professor Zhou, can you share your screen?
Yes, sure. I didn't get the previous one. Sorry. Okay. Can you see my screen?
Yeah, sure.
Let me try to do it in full screen. Is it okay if I do it like this?
Yeah. Thank you.
Okay.
So I think we can start the topic already. Professor, can you hear us?
Yes, but I can hear some echo.
Yeah, sorry about
Yeah, it's okay.
Okay, good. If you're ready, we can start the talk, I guess. Professor, can you hear us?
Yes, not very clearly. Can you tune the volume up a little bit, or you
Yeah.
can?
Is it
speed up a
better
little
now?
bit? Yes.
If you're ready, we can start the talk, I guess.
Okay, I can start. Okay.
Thank you.
Yeah, thank you. Thank you for inviting me to this exciting event. I hope every participant of Hackathon with success. It's true to know that this is a event exclusively for I think my part is exclusive for DKU students, so I can share something about my opinion and my research a little bit. So I will talk about robustness in machine learning and some of my research works. But before that, I would also like to talk a little bit about machine learning, right? Beyond the 101, what you will learn in DKU, right? So after you are so good at machine learning, right? What should you do? So I would first start with a view for career in machine learning. This is my personal opinion, so it's not you can choose not to regard it as a professional advice. Okay. So if you of course you can choose to do research after graduating, right? But if you want to work for a company or find a job, right? So probably there are two different roles that you can do with machine learning. One is machine learning engineer. I think for most participants in hackathon, this will be very interesting to you, right? Because you need to do a lot of coding. You need to be able to set up the infrastructure for companies, right? You need to build the system that incorporate AI. But this is also a red sea, right? A lot of people are competing for job positions. A different way is to work as a data scientist, right? Here you don't need to code that much, but you need to be able to analyze whatever data you have. And so I Googled it online because I'm already doing research. I'm not sure about the numbers if you talk about salary for data scientists. Okay, so I think there are different levels, right? If you, I think for most of our participants, if you are very good at coding, if you are very good at the course of machine learning, probably you can hit the last one, right? But even if linear regression is all you have, right, you can actually still be good at business analyst. There are so many companies, right, that are not based on technology, right? So some traditional industries, agriculture, right? They also need data scientists, and even linear regression can help them a lot. So usually these there are some companies not technology based. They have some small data science or machine learning teams, right? These are also ways you can contribute. Okay. But of course, if you are too good at coding, you should consider those big tech companies, right? If finding a industrial job is your ultimate goal. Okay. But on the other hand, if you want to do some research, or even if you are at some company, maybe you want to look at different perspectives of machine learning, right? Here are some of the keywords that you can choose to look at. So basically, statistical learning and machine learning are the same thing, right? So this is something that I always deliver to my students in my machine learning courses, right? So statistical learning is equivalent to machine learning, but you look at the same thing from different perspectives. If you talk about statistical learning, probably you are a data scientist, you are a statistician, right? You emphasize statistical principles, you emphasize mathematical background, right? How to make inference based on some principles. If you talk about machine learning, probably you are a computer scientist, right? You care more about how to build rigorous algorithms, right? How to implement them efficiently, right? Within your framework, within your hardware infrastructure, right? How to implement the best algorithm, right, in the most efficient way. Okay, so these are all the things you can consider. So if you look at the most recent decade or even 15 years, right? So there are some hot concepts, right, that basically every company is trying to look at. Robustness, right, is something that I try to talk a little bit, but there are also other concepts like fairness, right? If you are a company, you have some data, but the way you collect the data may be biased, right? For me, for instance, if you ask me to collect the data pictures of cats, right, I will take a lot of pictures of orange cats, right, which will overlook other types of cats, right? So fairness is also something important. Privacy, right? So if you want to collect data, this is something that you cannot avoid, right? This is also a very hot topic. For instance, even you use your cell phone, right? Your cell phone is constantly taking data from you, okay? But they have to write somewhere in the very long words that they will show you before you signing any software, right? There are some terms describing how they will keep the privacy. Some of the ideas or techniques are actually quite technical. Okay, actually there are a lot of statistical principles involved. There are also other things like interpretability. Right? This is especially important if you are a data scientist in a company which is not so technology based. So you need to be able to explain the results to your boss. This is probably something very, very important. Okay, but I cannot address everything in it. Probably, if you want to learn everything, you can take a course from me at DKU, right? Deep learning course or statistical learning course. So today I will only address one of the problems here called robustness, which means the ability of a model to perform well across different situations. Okay. Because in real life, if you collect data, there might be noise, right? Someone may want to attack you, attack your data, right? And if you want to apply something you learned for this domain to another domain, there might be a shift in distributions, and you cannot directly transfer your model. Okay, so all these have to do with robustness. So today, what I will talk about is important application called anomaly detection. So this is my own research work, and it's a joint work with Jesse Lai from Sony and Gilad Lerman from University of Minnesota. So Jesse and I used to be a student at University of Minnesota, and basically when he did his interview with Sony, he talked about research about anomaly detection, and seems that Sony find it very, very interesting. Okay. I mean, after he joined Sony, I always asked him for information about PlayStation, but he always refused to talk to me about anything like that. Okay, so what is anomaly detection? So anomaly detection is an application which aims to identify data points that do not conform to expected behavior, right? So in your collected data, there is something following a different distribution. For instance, if you have a computer network, there might be some anonymous traffic, right? This is called hack. I'm not sure in your hackathon projects whether you are asked to do something like that. There are also anonymous MRI image, which might be some signal for tumor, right? Of course, anonymous credit card data is everywhere, which means that you might be subject to some identity theft. Okay. So there are different types of algorithms under different settings. For instance, in the supervised setting, right, you want to train a machine learning model, and you have some label training data, both from the normal domain and from the anomalous domain, right? So you know what is normal, you know what is anomalous. But this is not very, very common, because usually you can't afford to predict what is anonymous, right? So usually the following two settings are more natural. The first one is unsupervised, which is also called outlier detection, in which you have no label at all. You are just provided with a data set. You don't know which part is normal, you don't know which part is anomalous, and you want to design an algorithm to find the normal data. The other one is semi-supervised or novelty detection, right? Which means you do know what is normal, right? But you don't know what is the potential outliers. So we actually did two different projects on these two different types of tests. Okay, so let's give more motivation to the first task, the outlier detection, right? This is actually quite common. For instance, if you Google Panda online, okay, Google will return a lot of pictures to you, okay? But most, if you just Google Panda, probably in your mind, you are talking about a giant panda, right? But what Google returns to you are not just a giant panda, right? There are some red pandas, which you can consider as outliers, right? If you believe the majority should be normal data, then these red pandas are considered as anomalous, right? And you want some algorithms that can detect them. So actually, there are quite a number of traditional methods that you can choose to do outlier detection. For instance, what's shown in this picture is called local outlier factor, or LOF. Okay, so the idea is actually very simple. You sit here, right? You sit at your location, right? And you look around. If you have a lot of neighbors, right? So probably you are normal. For instance, these numbers so these points with small numbers. But if you look around and you find no one is similar to you, then probably you are anomalous. For instance, this big circle with a large radius. Okay, so this is a very actually a very natural idea. But if your data is not just these two-dimensional points, if your data is complicated, then you need to find good representations for them, right? You need to be able to put them in this nice chart. So of course, nowadays, if you have complex data, you want to learn the main structures, you need to use some deep learning based model, right? Autoencoder is one such basic model. So the way we do anomaly detection using autoencoder is very simple. The idea is very simple. So we start with some data, right? We pass it through an encoder, then pass it through a decoder. Right? We try to reconstruct all the data points, but you actually cannot reconstruct everything perfectly because of the bottleneck in the middle, right? So if your latent space is a very low dimensional space, you cannot reconstruct everything. Then normally you would choose to reconstruct the normal data, right? So the normal data are reconstructed well. The anomalous data are not reconstructed well. So there would be a difference, right, in the reconstruction error. So by looking at the reconstruction errors, you will be able to tell which data are anomalous and which are normal. We can show this idea using a very simple example, a toy example of a Swiss roll. Okay, so this is a data set with data points in three-dimensional space, and the black points are considered as normal points, right? This has a shape of a Swiss roll, and the blue points here are actually sampled from a normal distribution. And I want to tell which of course I don't see the colors, right? I'm just given the locations of the data points, and I want to tell which are normal and which are not normal. So I implemented a autoencoder, and this is the reconstructed data, right? So we see that we roughly reconstructed the Swiss roll, but not exactly. So we can look at the reconstruction error, and of course there is a difference in distribution. But actually, the problem is that there is a big part where you see both colors, right? You see both normal data points and outliers with these reconstruction errors. So this means that an autoencoder is not enough, right? We have to improve it. And we can try to examine why autoencoder is not so good, not as good as what we expected, right? So we can look at the linear case if we cannot analyze the nonlinear autoencoder. Okay, so in the linear case, if you are familiar with deep learning autoencoders, right? You will see that autoencoders in the linear case is equivalent to doing PCA. Okay, and it's well known that principal component analysis is not robust. Okay, it's not robust to outliers. An example can be seen in this very simple example. Okay, you have a lot of points in 2D. Okay, I tell you the blue points are inliers and the circles are outliers. Okay, so technically, if you only look at the inliers, right, the main structure is actually this vertical axis. But actually, if you look at the outliers, you still do a PCA to find the one direction that describes the data. It will be something like 45 degrees, okay, which is quite different from the ground truth. Okay, and in the linear case, what we know is that we can use some robust metrics, some robust measure, right, to solve this problem. And the simplest way is to replace the L22 loss, right? Because if you do PCA, it's based on squared distances, right? So if we choose not to take a square of all the distances, then what we will get is L21 loss. This is known to be robust and is known to be able to handle arbitrary outliers. So if we do this, then we also get a version of autoencoder, right? It's just with a different loss function. And if we in this loss function, we actually embedded some robustness. Okay, so let's do the same thing. We still have a autoencoder, we still have a reconstruction error. It's just this time we have L21 loss instead of L22 loss. But if you actually follow this idea, you will not get a good result either, because this nonlinear setting is still different from the linear setting. Okay. So what you can do is actually what we did is to enforce some linear structure in the latent space. Okay. So in the latent space, we enforce a linear projection, right? And we use the so-called robust subspace recovery loss here. Okay, this is an error. This is an error for doing projection in the latent space, and we also have an error to enforce that what you do in the latent space is indeed a projection. Okay, so actually our loss consists of two parts. Okay, and this time it works well. Okay, so our loss consists of three parts. The first part is a L21 loss for the overall reconstruction. The second part is the sum of reconstruction in the latent space and a term that enforces the fact that A is a projection. Okay, so you can also observe what happens in this setting. We have the same input of a Swiss roll with some noise. And we choose to apply the encoder, the RSR layer, the decoder, right? So what you see at the end is something in picture D and E here. Okay, so D is the overall picture. You can see that a lot of blue points are thrown away from their original space. Okay, and if you zoom in to look at the original range of the data points, you actually see that the black points are quite close to their original positions. And this can be a better thing if you plot the histogram of the reconstruction errors. You will see that the normal data actually all have very small reconstruction errors, and the outliers have large reconstruction errors. You see from the picture that they are thrown away, right? Their final position are quite far away from their original positions. Okay, so this is what we did for the simple example. Of course, if we have some real data, we can also test our idea. So what we did is the following. So we collect some data sets, right? Each data set contains several categories. We choose one category as the normal data, and we randomly sample a certain ratio of outliers from all the remaining categories. And for instance, we have text data like Reuters, we have image data like Caltech 101, okay? And we see that if we implement what we proposed, which is called RSRAE, okay, we will get the top performance. If we use, for instance, just an autoencoder or autoencoder with L21 norm, right, we will not be doing so well. We can also compare with some of the other methods, for instance, the local outlier factors that we introduced. There are also some deep learning based models like one-class SVM, like DSCBM, DAC-MM. Those are all not as good as our method. There is a Git here. If you're interested, you can try. We are very happy about the result because the idea is actually very simple. We only embedded a robust metric, right, to commonly use the model, right, and we get some good results. So this is I mean, this looked quite fascinating for us. Okay, so that's one task. The other about outlier detections. The other thing we did is for the semi-supervised setting or novelty detection. Right, in this setting, we can train our model using normal data, and we in our test data, of course, we can have something normal. We can have something that are outliers. Okay, but our setting is actually more difficult. We considered a setting where in your training set, you can have some noise. Okay, so your training set is not pure. Okay, your training set is polluted. And in this case, we want to train something which disregards the outliers here. Okay, and this is a case that we're interested in. Okay. And our idea is also very simple. Actually, if you directly apply RSRAE, the previous model I introduced, to this setting, we can still do it because you can train an autoencoder using the training data, right? And the autoencoder is still there. You can use it for new data. This is probably also doable. Okay, but if we think it twice, right, then we believe that outlier detection is more like an instance-based method. So using autoencoder is natural, but novelty detection is more like a distribution-based task. So in addition to using autoencoder, we should consider distributions. So we used the variational version of autoencoder, the VAE. So a VAE is also a very commonly used machine learning model, right? So it contains, it's basically an autoencoder, but you need to do some sampling. And in addition to the reconstruction error, you have a KL divergence, which measures the difference between distributions from the latent space and your prior distribution. Okay, so taking this into account, we can prove some results that may be interesting for statisticians, right, or mathematicians. But our model is like this. So you have some training set, right, which are probably polluted. You encode your data into two different distributions. Okay, you try to encode the inliers into this big mode in the Gaussian mixture, and you encode the outliers into this small mode of a Gaussian mixture. Okay, so this is what you try to learn. And when you do your inference, you only use the major mode. Okay, you only use your major mode. So if we can do reconstruction well, right, which means your data falls into this major mode, which hopefully learns the normal data here. Okay, if your reconstruction is not has a large error, and probably your data do not fall in this inlier mode, and is probably an outlier. Okay, so this is basically our idea. So there are some mathematical techniques which probably I should just skip. Okay, so there is something called Weserstein distance, and we did some analysis to try to persuade ourselves why this W1 is so robust. This is again a robust metric, a robust measure that we use in this task. Okay, and we still did some experiments, which shows that our idea is still doing well. Okay, so we actually wrote a first draft of this article 2 years ago, maybe, but it's recently published. We tried hard to persuade people, and you can see it's published in ASS. Probably some statisticians are interested in the concepts. Okay, but actually, in terms of performance, we are actually doing well. If you look at the blue lines, they're almost always on top. Okay, and we did some analysis, try to show people why Weserstein distance helps. But I see that we don't have much time, so let's just safely skip those. Okay, those analysis. I would be happy to discuss this with you if you're interested in the theory. Okay, but you can definitely see more if you look at these two papers that we wrote. Okay, so given time, I want to say thank you for again for having me. And if you have any questions, please feel free to let me know.
All right, all right. Thank you so much, Professor, for amazing presentation. Do we have any questions from the hall? All right. Okay, there's so far no questions from the hall. Yeah. So I guess, yeah, so this was the last speaker session of the hackathon before we move on to the awarding ceremony. Again, I would like to thank you, Professor Do, for this amazing presentation. Think this was very in detail presentation, which is useful for anyone who is interested in machine learning. Yeah. So yeah, I'd like to say thank you for that.
Yeah, thank you. Thank you again for having me, and
Thank you so
enjoy the
much.
rest of the day.
All right.
Bye-bye.
Bye-bye. Yeah.